A warm welcome to all the dignitaries of National Instruments, to the staffs and all the students who are presently watching this video. We, the team members of Anayantra contest, team ID NY188, are here to present our project progress report on Surakshit, a smart safety wear for two-wheeler riders. I, the team leader Rajavel Murugan, and along with the members G. Sriram, N. Sharan and M. Puvarasu are present here right now. First, let me introduce you to our project. Surakshit, by the name it suggests, Su means better and Rakshit means to safeguard. Our project is mainly worked on a motto, alert today and alive tomorrow. The four modules present in our project are trigger on helmet detection, back level analyzer, overspeed alert system and cellular phone jammer. Before starting with anything, first let me explain you about the overall connection blocks. Here, as the vehicle key is triggered, we have two units that get activated. One is the helmet detection unit and the other one is the back level indicating unit. And upon these, there are two choices on which the engine may remain off or the engine may ignite. And based upon the engine ignition, we have the other two units, that is the jamming unit and the overspeed alert units, that can also work upon these three conditions. First, let me explain you about the trigger on helmet detecting unit. In the trigger on helmet detection unit, our main interface is MyRayo from National Instruments. The input consists of a camera that can detect our face, and the output consists of an engine controller switch that works according to the conditions given. That is, the engine may ignite when the helmet is existing and the engine will go off when the helmet is not existing. And based upon this, we have worked on the vision assistant module in LabVIEW. In this, we have worked on the two principles of object tracking and color pattern matching with our helmet. Here, for an example, we have taken the Vegas helmet for our project that stands as an example. And here I'm going to run this in a loop. This is me sitting over here with that helmet. And as you can see here, the object tracking module consists of the helmet's pre-stored image. And the color pattern matching is nothing but the Vegas trademark symbol that is present over here. Here you can watch a big red block that is tracking the helmet and a smaller red block that is tracking the Vegas trademark. So based upon this, when the helmet is present and the helmet is worn by the rider, the vehicle is allowed to start, and when the helmet is not worn by the rider, the vehicle will remain off. So now let me close this VI. Now let us continue with the back analyzing unit. In the back analyzing unit, the interface is also MyRayo. In the input section, we have a sensor called as the MQ3 sensor, which is present at the mouth vent of our smart helmet Surakshit. And in the output section, we have the engine controlling switch and the engine. The conditions on which this module works is that when the back level is below 0.08, the engine will be ignited, and when the back level is greater than 0.08, the engine will remain off. The meaning of back is blood alcohol content. The optimum level and the legal level for the blood alcohol content in our body during driving is 0.08, and based upon that, we have worked on this condition. Now let me explain you this module in terms of LabVIEW VI. Since we don't have this MQ3 sensor input in LabVIEW, we have just taken it as a control using this control buttons, and now just let me run this continuously. So what you can see here is the MQ3 sensor input. Here the digital read that corresponds to the reading of the sensor, and here you can see the four LEDs that basically corresponds to the back level above optimum levels and the back level below optimum level. If the back level is above the optimum level, the engine should remain off. That is a prime condition. And when the back level is below the optimum level, that means the engine should turn on. So now just let me take it till 0.075. Until then we can see that the back level condition is under optimum levels and the engine is still on. When I take it to a level greater than 0.08, immediately we can see that the back level conditions are above the optimum levels, and that the main condition satisfying our criteria is that the engine should be turned off. So this is how we have designed the back level analyzing unit using LabVIEW. So let me just abort this execution and let us move on to the next module. What we are going to see here is the overspeed alert system. In the overspeed alert system also we have the MyRayo interface, and in the inputs we have the three conditions from the speedometer, and in the output you have your helmet having the view pin LEDs, that is the tricolored LEDs having the yellow, orange and red, and along with an audio assistance. Here we'll be dealing with the three conditions, that is speed range between 60 to 80, from 81 to 120, and also from 121 to 240. Based upon the critical level, based upon the increase in the critical levels, we have made the tricolored LEDs into three ranges, that is the yellow, orange and red. The duration for each alerting system will be 10 seconds with a time interval of 30, 20 and 10 seconds respectively for each of the levels. And the beep sounds or the audio assistance that will be assisting with this output of the tricolored LED will have a frequency of 1, 0.5 and 0.33 Hz respectively. Now let me explain you this in LabVIEW, that is the overspeed alert system. Here what you see is the block diagram of the overspeed alert system consisting of the input as speedometer, and these three while loops what I have put over here is for the extreme overspeed level, and this is for the moderate level, and what you see down over here is for the average speed levels. Here what I have used is lower limit and upper limit values, and in each of the while loops it follows the same principle. Now let me explain you this with the front panel system. So, and let me run it in a continuous way. So until I go on till 59 kmph, I won't have any indication, and during that time the rider of the bike will not be disturbed by any kind of alerting units present over here. And as I pass on to 60 to 80 km per hour, I'll have the tricolored LEDs getting activated, where the illumination will be based upon yellow color. Fine. And as I cross after 80 and reach till 120, I will have the activation of the orange colored LEDs in the view pane that will basically illuminate my pane, telling the rider that he is going in a critical speed and that he wants to slow down. And this process will be continuing for about 10 seconds with a time interval of 20 seconds. And if I'm too excited, or if I'm too happy, or if I'm not at all well, and if my reflexes won't work well together, then of course I'll be crossing more than 120. And in case of such overspeed situations, the tricolored LEDs will activate the red color, and based upon that you'll also have an audio assistance. And regarding this, the duration of this overspeed alerting system will be about 10 seconds, and the time interval will be also 10 seconds. The reason why we have put it as the time interval as 10 seconds is that because when the driver continues to drive in a range of speed greater than 120 for a long time, he has to be intermitted immediately from time to time. So for that we have reduced the time interval levels to 10 seconds. And regarding this, what I have put here as an output is that the three LEDs showing you the three different colors, and along with this we can also have an audio assistance, which I have created it as a sub VI. that is this will be my audio output system. In this, based upon the true or false condition that the whether the driver is in the particular speed limit or not, uh, the input will be gone through this, and based upon that we'll have an audio assistance file over here, and this sub VI will be connected to the output of this overspeed alerting system in this while loop, and accordingly we'll get the corresponding audio outputs that are required to alert the driver on specific speed conditions. Fine. So the next section that we'll be dealing with is the cellular phone jammer, and the mode of operation that a cellular phone jammer works on is that as soon as the engine is ignited, the jammer will be switched on, and the rider will not have any disturbances caused by the mobile phone while he's driving. The method of action that is followed by the jammer present in the Surakshit helmet is the denial of service. And when the engine is switched off, naturally the jammer will also switch off. And the frequency range that we are working on is 900 megahertz to 1950 megahertz to jam all possible signals that are actually incoming for the various kinds of mobile phones that the user uses. And this is just a small representation of the jamming unit, the jammer that is present at the nape of the Surakshit helmet. Now let me explain you this on the VI that we have created. Jamming. What I have over here in the front panel is the frequency control, and here is the amplitude control. The frequency control is made for generating a sine wave, and we have added a noise waveform along with it, and the combined wave will appear over here. And based upon the working condition of this jammer, when the frequency ranges are between 900 and 1950, the jamming signals will be activated, and based upon that the jamming process will be on. And if it is under 900 megahertz, the jamming process won't run. So first let me run you this and show. Let us first set an amplitude, for example 262 or something like that, and let me take you until and unless I have reached 900. You can see that here we have a range of 500 to 899, and until that the jammer is not at all tuned, but we have the generation of the jamming wave which cannot jam the incoming signals right now. But as I take it to a frequency greater than that, that is from 900 to 1900 or 1950 whatsoever, you can see that the jamming process is on. And when this kind of signal at a high power but at the same frequency as that of the incoming signal reaches the microstrip antenna of all the cellular phones, then you can deny the service of that mobile phone of whatever network he uses. And this is the block diagram of the jammer that we have presented over here. The added noise waveform is nothing but a white Gaussian waveform, and the frequency generated here is nothing but the sine wave, and this is the block of that jamming wave. So until this, what you have seen is nothing but the different modules present in the Surakshit Smart Helmet version 1.0, and based on that, let me also explain you and give you a gist of what is the overall system diagram of Surakshit 1.0. At the center you can see the MyRio interface that will be dealing with all these different types of modules present in the Surakshit Smart Helmet. Here you can see the first module, that is the trigger on helmet detection unit, that is the whether is detected, that is whether the helmet is detected or not, and based on that you have these inputs, input 1, input 2, and accordingly you will have your output here as whether the engine should be on or off. And the second module, which consists of the back level analyzing unit, that consists of the MQ3 sensors placed at the mouth vent of the Surakshit helmet. It will also consist of two different choices of whether the engine should be on or off based upon the back levels. That is, whether it is greater than 0.08, the engine should remain off, and if it is less than 0.08, the engine should trigger on itself. And the third, what you see here is nothing but the speedometer unit, where the speed levels are set over here, and based upon that you have these three inputs from these three readings, A, B and C, and corresponding to that you will have the three outputs over here, A, B and C, where LED fixings are there to illuminate the view pane, and along with the audio assistance or any kind of buzzing or beep sound with specified frequencies. And in this overall system diagram we have eliminated the jamming unit, since under any aspects it is not connected to the MyRio interface structure. Alright, so far what you have seen is the overall system diagram, and now just let me end it up briefing you on the impacts and goals of what Surakshit wants to achieve. So as engineers, our prime goal is to cut down the death rates caused by the helmet absent and road accidents. And based upon this, why version 1.0 of Surakshit has these four basic modules is that most of the accidents that occur on roads are due to the failure of certain things that are based on these four modules. That is due to talking over the cellular phones, that is due to overspeed driving and without wearing the helmets, and also drunken driving. So we have, according to our survey, what we have seen is that there are a large number of brain deaths caused to the youngsters of our very own country, which is actually a very one of the sad incidents to be taken by us. And because of that problem, and in order to eradicate that kind of issues, we have taken a decision to undergo this project called as Surakshit. As the name suggests, it should lifeguard the people, and based on the road journeys. And all we want to say is that, and all we want the public to say is that, when Surakshit is on, fears are gone. And that's all. Let's end up the session over here. Thanking you, the team leader, Rajavel Murugan, and along with the team members, G. Sriram, Sharan and Puvarsu M, Team ID NY188, Yantra 2015, Jansen's Institute of Technology, Coimbatore 59, Tamil Nadu. Thank you all. Thank you very much.